Hey everyone, welcome back to Axiom. Today we are diving deep into DDL, DML, DCL commands. This is one of those concepts in database management systems that a lot of students struggle with. So I wanted to break it down for you in the simplest way possible. Let's get right into it. In computer science, merge sort provides a flawless mathematical guarantee, a worst case time complexity of O and log n. Time complexity is a metric that measures how an algorithm's runtime scales as the input size grows, no matter how chaotic the data. Merge sort never exceeds this boundary. In contrast, quicksort carries a notorious O n squared worst case risk, where a specific data pattern can cause the processing time to collapse, yet the standard library sorting functions in C, C++, and Java tell a different story. When sorting standard arrays, the developers of these core systems almost universally default to the mathematically vulnerable quicksort instead of merge sort. This creates a massive gap between textbook theory and professional implementation. We have to reconcile why the architects of our most heavily used languages would deliberately choose an algorithm with a known fatal flaw over a mathematically perfect one. Theoretical time complexity is a useful mathematical model, but it ignores the physical behavior of the hardware. In production, the way silicon and electricity interact with memory can invalidate even the most elegant mathematical proofs. Algorithmic performance relies on physical layout. An array is a contiguous block of memory. Elements are stored directly adjacent in RAM. A linked list uses scattered non-contiguous nodes. These disconnected nodes are held together by pointers which locate the next element in the sequence. An algorithm is a logical set of instructions, but its execution speed is dictated by which of these two physical layouts it is forced to traverse: hardware architecture. The way a system allocates space and moves data between physical addresses is the ultimate judge of efficiency, often overriding pure math. To see why merge sort is so highly regarded on paper, we have to look at its divide and conquer framework. The algorithm recursively splits a dataset in half until it isolates individual elements. This recursion tree maps that process. We start with the total input size n at the top and continuously divide until we reach the base cases of 1 at the bottom layer. Because the dataset is cut exactly in half at every step, the total vertical height of this tree is strictly bounded by the mathematical function log base 2n. At each horizontal layer, the algorithm executes its merge subroutine. The combined work across any single horizontal layer is always directly proportional to the total number of elements n. We represent this as Cn, where C is a constant unit of work. The total computational cost is found by multiplying the work done on each layer Cn by the total vertical height of the tree, log base 2n. This tree structure translates into a formal recurrence relation, C of n equals 2Cn over 2 plus centimiogen. This states that the time to cross Sn elements equals the time for 2 halves plus the linear cost to merge them. By applying case 2 of the master theorem, we mathematically confirm the absolute theta of n log n bound. On paper, merge sort is optimal, it scales gracefully and carries a guaranteed logarithmic ceiling that it will never pierce, regardless of how the input data is ordered. But mathematical theory assumes that moving data is free. Physical hardware tells a different story when we attempt to merge contiguous arrays. Merging two contiguous arrays in place is computationally destructive because the memory block is solid. Inserting an element from one array into another requires shifting every subsequent element over by one slot. This constant shifting ruins the time complexity. To avoid this shifting, merge sort forces the operating system to allocate a completely separate auxiliary array to hold the sorted results. This creates an O of n auxiliary space complexity. Space complexity measures the amount of extra working memory an algorithm requires. For massive data sets, stopping the CPU to allocate and deallocate blocks of RAM creates a heavy computational penalty. It also creates a hardware bottleneck regarding cache locality. Cache locality is a principle where a CPU runs significantly faster when it reads data clustered closely together in physical memory, avoiding slow trips back to the main RAM. Because merge sort requires that auxiliary array, the CPU must constantly jump between two separate physical locations in RAM. This breaks cache locality and causes severe cache misses, stalling the processor. Quicksort behaves differently. It swaps array elements directly in place. The CPU locks into a single contiguous memory block, writing the hardware cache perfectly. For arrays, the physical cost of O of n memory allocation and cache misses outweighs merge sort's mathematical perfection. On contiguous silicon, Quicksort wins. If we change the data structure to a non-contiguous doubly linked list, the physics of these algorithms invert. Linked lists lack O of one random access. Random access is the ability to instantly jump to any specific index, like the middle element in a single step. This lack of random access destroys quicksort. Quicksort relies on picking a pivot and swapping distant elements. On a linked list, finding that pivot requires a linear traversal, reading node by node. Merge sort is immune to this. It processes data strictly sequentially, reading from the front of the list to the back. The merge step on a linked list is different. Two sorted lists can be merged through pointer rewiring. The addresses stored in each node simply detach and reconnect in the correct order. Because the physical nodes are already scattered across memory, they never move. There is no need to shift data or allocate a new auxiliary array. This rewiring drops merge sort space complexity on linked lists from O of n down to a perfect O of 1 in place execution. Freed from the memory tax of auxiliary arrays, merge sort finally achieves its theoretical speed on actual hardware. For linked lists, it is the undisputed champion. We can visualize this engineering reality by comparing these two algorithms against the two memory structures in a simple matrix. In the array column, quicksort wins. Its in-place swapping leverages cache locality, while merge sort is penalized for its extra memory requirements. In the linked list column, the results flip. Merge sort wins through pointer rewiring, while quicksort suffocates without instant random access. That's a wrap on DDL, DML, DCL commands. I hope you now feel way more confident about this concept. If you do, show some love, like, comment, and subscribe to Axiom. Every subscription genuinely motivates me to keep making these videos for you. See you in the next one. Take care.